In the last video, we were working on constructing a linear approximation for a function that could be described as a product of two functions, and we saw that we could find its linear approximation in two ways. We could either take the linear approximation of the product of the two functions, or what we could do was that we found that if we knew the linear approximations for each of the functions, that we could take their respective linear approximations and multiply them together. And we got the same answer. And I said I wanted to show you that this is the case in general. So that's what this video is. We're going to prove that that is the case in general. So just real quick before we start, let's just explain some notation here. So on this left-hand side, it says find the linear approximation of the product of two functions. And then on this right-hand side, it says take the linear approximation of f and multiply it by the linear approximation of g, and then take the linear approximation of that product. So that's what we want to prove in this video. We want to prove that this equality is true in general. And before we begin here, let's just get one small house cleaning thing out of the way. F and G, we are assuming are differentiable functions. These are differentiable functions. So with that out of the way, we can begin. So let's first tackle this left-hand side. Again, maybe I'll ask you to pause the video for a few things. So why don't you find the linear approximation for this product of two functions, f and g, f times g. So that is going to be, again, we want to do that in general. So I want you to find this. For x values near some x naught, find the linear approximation of f times g. What is that going to be? So pause the video and find that out. All right, assuming that you've given it a go. Again, we've been working with this. Should just be review here. We're going to apply the linear approximation formula. So we are going to say that f of x naught times g of x naught. And then we are going to add, and then we need to take the derivative of this product of two functions, so we need to use the product rule. And we're going to evaluate the derivative at x naught. So let's take the derivative using the product rule. So we have f prime of x naught times g of x naught plus f of x naught times g prime of x naught. And then all of this is multiplied by x minus x naught. And again, this right here is just the derivative of, this is the derivative of f of x times g of x, and then evaluating it at x naught. That's all this is. So again, that's just a standard linear approximation formula, and we can, under our notation, we can call this guy right here is L of f times g. Linear approximation of f of x times g of x. Again, that's what it's saying. So that's the left-hand side, and now let's move over and start talking about this right-hand side. So we need to find the linear approximation of f. Let's do that next. Let's find, and this is going to be, again, for x values near some x naught, we want to find the linear approximation of just f. So again, you can pause the video, but here we go. So we have, again, f of x naught plus f prime of x naught times x minus x naught. So that's what we find for L of f. That is this right here. This is L of f. And now we're going to do the same thing for g. So again, for x near some x naught, g of x is going to be approximately g of x naught plus g prime of x naught times x minus x naught. And again, this guy right here is the linear approximation of g. So according to the right-hand side, we need to multiply these guys together and see what we get. Let's do that next. Grab some more space. So we are now going to take the linear approximation of f that we found and multiply it by the linear approximation of g. So let's write that out real quick. F of x naught plus f prime of x naught times x minus x naught. And all of that is going to be multiplied by, we have g of x naught plus g prime of x naught times x minus x naught. Okay, so let's multiply this guy out and see what we get. So we're going to get f of x naught times g of x naught. And now let's go here. So we have f of x naught times g prime of x naught times x minus x naught. And now we'll go here. So we have plus f prime of x naught times g of x naught, and then times x minus x naught. And then lastly, we have this guy right here. So we have plus f prime of x naught times g prime of x naught. And I'm running out of space, but we have an x minus x naught squared left over. So we'll put that guy down here. Okay, so again, this is the linear approximation of f times the linear approximation of g. And let me scroll back up. This right-hand side says we need to take the linear approximation of that. So what does that mean? What does that mean? Well, again, like in the last video, we said we need to toss out these higher order terms here. We're looking for a linear approximation. So anything higher than a linear term here, we are going to toss out. And that means that this quadratic term goes away. Peace out, man. So let's just simplify this and try to get it to match to what we had up here. So I'm going to factor an x minus x naught out and see what we get. So we have f of x naught times g of x naught plus, now I'm going to factor an x naught out and I'm going to put this guy first. So we have an f prime of x naught times g of x naught plus, we have this guy here. So we have f of x naught times g prime of x naught. And then we factored an x minus x naught out. So we have an x minus x naught out here. And this guy right here, let me see if I can scroll up and get them both on. This guy right here, this guy down here, this guy right here is exactly what we got up here in yellow here, L of f times g. So we got the same answer and we've proven this equality now. And again, there's a ton of notation going on in here, and we said x naught quite a few times in this video. I don't want you to lose fact of, really you should think of the last example here, that you can find a linear approximation using both of these methods here. So if you know the linear approximation for the product of the two functions, if you know their individual linear approximations, you can just multiply those together, and you can see that now that is the case in general here, that you can do that. So that's what I really want you to take away. And in the next video, we're actually going to see that this is the case for quadratic approximations as well, and that is going to be a little more useful for us in some upcoming videos.